Hi guys, welcome to week 10 of Psych 3330 Elementary Statistics. This week we're going to talk about t-tests and how you do t-tests with independent samples. We'll see exactly what that means in just a second. So what we're doing is basically the same hypothesis testing stuff that we've been doing for several weeks now. So it's not going to take long to go through this. We're just going to extend that technique to one specific situation. Particularly, we're going to extend it to the situation where you have an experiment very similar to the following that I have depicted on the screen. So let's suppose this time we got a little bit different variation of this memory experiment that we've been doing all semester. And the variation goes as follows. You have your memory patients, and instead of just giving them all a treatment, we're going to see if the treatment really is having an effect on people by comparing it to a placebo. Okay? So in a sense, what you now have is what's called a between subjects design, where you have your patients going, half of them going into one group. This one group gets the memory treatment, and then the other half goes into the other group, which gets a treatment that's not really going to have an effect. It's just a placebo. And so then you give both of them a memory test, and the question is, are these memory test scores different? That is there an effect of this treatment as compared between these two independent groups? So down below you can see the null hypothesis for this situation would be that they are the exact same. The null hypothesis would be that they're different. Okay, so the basic idea is we want to compare these two means. Now, if you think back before when we did t-tests, or even z-tests for that matter, what we did was we took a single sample mean and compared it to a known population mean. Well, this time it's a little different. We're going to compare two sample means, two independent sample means. And to do that, we're going to use something called the independent samples t-test. This is something that you can use when you have two samples and the samples are independent. That is, they are different treatments, different people, independent in every meaning of the word independent. Now, this is the formula for the t-statistic, and we're going to spend some time breaking down what this formula is. It looks a little more complicated than before, but what I want to convince you of in just a second is that it's precisely the same formula. It's just the notation makes it appropriate for this situation where you have two different groups. So instead of explaining the formula now on this slide, let's go and kind of mirror it with our traditional t-statistic. So over here on the right, if you'll look at the one sample t-test, this is what we did last week. Remember, the basic idea is it's just a z-score, right? What you do is you take the sample mean, compare it to the population mean, and you divide by this standard error. Remember when you see this S with the X mean under it? That's the standard error. Well, you're going to do exactly the same thing in the independent samples t-test. What you've got here on the left, this thing that's XA minus XB bar, that is just the difference in the observed sample means. Okay, so that's just still the sample stuff right there. This stuff on the right is still the hypothesized population mean, just like before. Now, you had something similar to this last week, if you remember. When we did a paired samples t-test, we had a very similar formula. And if you'll remember, the null hypothesis says that this mean and this mean are going to be the same, right? That there's no difference between the population means. And so in that case, typically what happens is that this little quantity right here, this mu A minus mu B, is equal to 0, because we're supposing that those two means are equal, and so when you subtract them, you get 0. Okay? And then finally, we've got this little thing down here. This is just, again, the standard error. That's that difference we would expect by chance. Now, standard error we know how to compute. On the one sample case, it's very easy. You take the standard deviation and you divide by the square root of the sample size. Okay, we've been doing that for several weeks now. This one is not quite so easy, because the problem here is that we have an estimate of standard error that's based on two samples. All right, and each sample has its own standard deviation. So the question is, how do we combine those two sample standard deviations into one standard deviation, if you will? Okay, and the answer is through something called pooled variance. All right, and so right here what you have is a formula, and you can write this formula down. This is not something I expect you to commit to memory. In fact, in about a week I'm going to give you a sheet that has all these formulas written on it anyway, but feel free just to write this down on a piece of paper. This is the total formula for the standard error in a independent samples t-test. Now we got to break this down just a little bit. First of all, The thing that's circled in blue up here, this SP squared, this is something called pooled variance. Now, pooled variance is the variance you get by taking the variance from sample A and the variance from sample B and combining them together. You can think of it as an average. We'll get to that in just a second, but it's essentially a combining that makes sense. All right, so it's called pooled variance. So what we do to find the standard error is we simply take the square root of, well, we just take the pooled variance over the first sample size plus the pooled variance over the second sample size. And we'll see an example of this as well as in the practice lecture later. So the question now is, we know what all this stuff is except for this pooled variance. So how does one find pooled variance? Well, the first formula I'm going to give you for pooled variance is going to scare you. All right, here it is. This is pooled variance. Whew. All right, what is all this stuff? Well, let's see. Pooled variance is what you get when you take, let me not highlight all that stuff, hang on. When you take the variance from sample A times the degrees of freedom from sample A, plus the variance from sample B, plus or times the degrees of freedom from sample B, over the sum of the degrees of freedom for both samples A and B. That's a mouthful, right? Again, that's why it's good to write this stuff down. And so you can get this, you know, if you just find the variance of sample A, find the variance of sample B, you know how many participants are in each section, each sample, so you can find this, right? Well, we're gonna use a little bit of mathematics here, a little very simple algebra, and actually simplify this formula quite a bit. All right, so let's try to do that. The first thing that I want you to notice is that each of these has a common form, right? Each of these terms in the sum looks like variance times degrees of freedom. Now I want you to remember, of course, that degrees of freedom is nothing more than the sample size minus 1, so keep that in mind. Now remember, back when we learned how to find variance last week for samples, variance is simply the sum of squares divided by n minus 1, okay? Remember, it was sum of squares over n as long as it was a population, but for samples, the variance is the sum of squares divided by n minus 1. In a sense, it's that average squared deviation. Well, here's what I want you to notice. If you took this expression and then you multiply both sides by n minus 1, you would get something like this on the bottom. S squared times n minus 1 equals SS. All right, so I'm just taking that and rearranging it. Well, what is n minus 1? N minus 1 is the same thing as degrees of freedom, right? So if we move up to here, we get this equality. We get the S squared, the variance, times df equals SS. All right, now it's nothing more than a rewriting of this original variance formula. But this is nice, right? Because this says that anytime you have something that looks like S squared, variance, times df, like you do up here, that's just the same thing as the sum of squares. So what that means is that in this complicated formula for pooled variance, what I can do is replace the complicated part, namely this SA squared times DFA, with just the sum of squares for A. And if you do that same thing for the B term over here, you get a much nicer formula down here for the pooled variance. So on formula sheets, etc., this is the one I tend to give because this is the easier one to it's the easier one to remember for me, and it's also the easier one to use. It basically says to find the pooled variance, all you got to know is the sum of squares for A and B and the DF for A and B, and then you can combine them together. Right? You actually don't even have to go through and find the variance for each group. So that saves you a little bit of work. So this is the one I would recommend writing down, not this one. They are mathematically the same. We just showed that, but I would definitely use this bottom one. So why are we doing that? Well, what we're doing is we're getting an estimate for standard error based on this formula here, and that formula uses this notion of pooled variance. So a lot of computation this week, but all that computation is just going into finding our t-score the same way that we've always done. Okay, so here's what we do. We compute our standard error this way. Okay, this is the square root of pooled variance over NA plus pooled variance over NB. What is the pooled variance? Pooled variance is this formula right here. T statistic, you just simply compute this. As long as you know your two sample means, this is going to be 0. You've just computed your standard error up here, then you got your T statistic. The last thing you need to know, remember with a t-test, your critical t-value depends on the degrees of freedom. So how do you find the degrees of freedom? Well, what you do is you combine the degrees of freedom for both groups. All right. So what that means is the total degrees of freedom is going to be the degrees of freedom in group A plus the degrees of freedom in group B. All right. And as a formula, that means that the degrees of freedom is just, well, NA minus 1 plus NB minus 1, which is the same as NA plus NB minus 2. Okay. Now, we'll talk a little bit in the practice lecture about what that means, but that basically means that if you had like 15 people in each group, you lose 1 degree of freedom for each group you're comparing. So overall, you would have a sample of size 30, 15 plus 15. You would lose 1 degree of freedom for this group, so you're down to 29, and you'd lose 1 degree of freedom for this group, so you'd be down to 28 degrees of freedom. So that's the one that you would use to look up your critical value in the t-table. Okay? So a lot of formulas. Again, write them down, use them. Okay? I don't expect you to memorize this stuff, but I do expect you to know the process. So let's go through a quick example, and then I'll also show you how to do this example in SPSS. So Dr. Mnemonic develops a new treatment for patients with a memory disorder. He isn't certain what impact, if any, it will have. To test it, he randomly assigns 8 patients to one of 2 samples, a control group and an experimental group. He then gives one sample the new treatment, but not the other. Following the treatment period, he gives both groups a memory test, and these data are presented down here. We want to use alpha equals 0.05. So here's your 2 groups. Okay, first thing we need to do is we need to compute the mean and the variability for each sample. Now what that means is we compute the mean, and then we also compute the sum of squares. So you remember how to do that. You find the mean, find the deviations, and then square up all those deviations and add them up, and that's your sum of squares. So we'll do that for the control group. So we get a mean of 50 and a sum of squares of 250. Do that for the experimental group. We get a mean of 44.5 and a sum of squares of 155. Now we've got everything we need to compute the t-test. All right. Remember degrees of freedom, that's going to be the sample size minus 1 for each of these. So that's going to be 3 on the control group and 3 on the experimental group. Now, the first thing we need to do is we need to find the pooled variance. Remember, we need to combine the variances together. And we had a nice formula for doing that just a little bit ago. We take the 2 sums of squares and add them up and divide by the 2 degrees of freedom. So this would be 250 plus 155 over 3 plus 3. Gives you a pooled variance of 67.5. Okay. Now we want to find the standard error using that square root formula. So square root of pooled variance over NA plus pooled variance over NB. So we'll use that pooled variance that we just found, 67.5 over 4 plus 67.5 over 4. Take the square root of all that, and we get a standard error of 5.81. And then finally, we're able to find our t-statistic. Our t-statistic is the difference between the 2 sample means, so 50 minus 44.5, compared to a hypothesized difference of 0 over the standard error of 5.81. So we take this difference over 5.81, and we get a t-score of about 0.95. Now, of course, you've done this enough now to know that's probably not enough, but we don't yet know the critical t-value. So the question is, what t-value are we going to use for our critical? Well, our degrees of freedom total that we're going to use is 3 plus 3 is 6. All right? So we're going to, just for the heck of it, look up a two-tailed test. The degrees of freedom total will be 6, and we go in our table and we find that the critical t-value is 2.447. Our observed t-value is only 0.95, so what that means is we're not extreme enough, and hence what we do is we fail to reject the null hypothesis. Okay? So that whole process, that whole hypothesis testing thing, that's the same. Now, all you've got to learn new for this week is how to use these new formulas. You don't have to learn the formulas, you just have to learn how to use them. Okay? So just to recap, let me go back through here. Just to recap, first thing we do is find the means and the sum of squares if they're not already given to us. Then we find the pooled variance using this formula. Then we find the standard error using that pooled variance that we just found. And then finally, we can find our t-statistic. All right. So that's the only part that's new. Okay, I want to show you real quickly at the end of this video how we would go through and do this on SPSS. Now, I'm starting with a blank SPSS workbook because what I want to do is show you the wrong way to do things. All right. So I'm just going to go into the data here, and here's the data once again, 45, 55, 40, and 60. The naive thing to do would be just to set them up like you saw them in the table, right? 43, 49, 35, and 51, and try to do some sort of t-test. You're going to pick around a little while, and you're going to find that this is absolutely the wrong thing to do. Because the way SPSS views independent groups data is as follows. You have to have one variable that is your dependent measure. That is your score on this memory test or whatever. You have to have another variable that's called your grouping variable. All right, so that's where you're going to specify whether the scores in this first column belong to the control group or to the experimental group. So what I'm going to do to simplify things here is I'm going to go to variable view. I'm going to name these variables a little bit better, okay? So the first variable I'm going to name is my mem score. All right, so just memory score is all that means. The second variable is my grouping variable. So I'm just going to call this group. All right. Let me get rid of all that. Group, okay? And I'm going to go over here and change things just a little bit. First of all, the measure, this is a nominal variable, right? This is not a ratio variable. So I'm going to call it nominal. And I'm going to give it some values as well. So if I click this little box under values, I can say that I'm going to assign the value 0 to my control group. Oops. So I'm going to click 0 and then add. And then I'm going to assign the value 1 to my experimental group. This will just help me in my output here in just a second. All right. Now I can enter the data. So I don't want raw scores there. So the scores in the control group were these 45, 55, 40, and 60. The scores in the experimental group were 43, 49, 35, and 51. Now I have to go over here in the grouping variable. The control group I label as zeros, and then the experimental group I label with ones. So this is a prototypical sort of independent groups type labeling in SPSS. We'll do the same thing next week when we do analysis of variance. So, all right, so now we've got the data in. Let's go and do the independent samples t-test and see if we get the same output that we got on our slides just a second ago. So to do this, I'm going to go to the Analyze menu, Compare Means, and you'll notice there's an independent samples t-test. So what do we do? Well, it's asking for test variable, or Z, all right, so there's just one in this case, as well as a grouping variable. So the memory score is my test variable, the group is my grouping variable. Now it's got some question marks. That means it's asking me to define groups. So real quickly, group 1 is going to be the group 0, and then group 2 is going to be the one I labeled 1. Okay. All right, and then we can just hit OK. And then we'll move the output into the window so that you can see it. Here's our descriptive statistics. Here's our mean for the control group and the mean for the experimental group. That's exactly the same thing that we just got. Let's go down here to this independent samples t-test. There's a little bit more output here than what you need, but just pay attention to the first row. Okay, if we go over here, we get a t-score of 0.947. If you'll remember from the lecture, we got, let's see, oh, there it was, 0.95, right? So we got almost exactly the same thing. Degrees of freedom was 6. The significance, remember, if this is less than 0.05, then we can say it's a significant difference, which means we reject the null hypothesis. This is not less than 0.05. This is much bigger, and so we fail to reject the null hypothesis. So as you can see, we get exactly the same output in SPSS that we got doing it by hand in our lecture. So that's how you do an independent samples t-test. The practice lecture will have 2 or 3 examples of this computation. Again, the only thing different is you've got a new formula. You've got to deal with this notion of pooled variance now. Once you get that, it's really not too bad. Remember, write those formulas down in a safe place. That way you can come back to them and use them when you need them. So for now, that's all for week 10. That's all for t-tests. And next week, we'll move to something even better called analysis of variance. But until then, we'll see you next time.